Matrices, we're actually going to talk really quickly about identity matrices. So that's our first slide. Okay. Things to note about an identity matrix. An identity matrix must be square, so it has to be n by n. And the idea behind the identity matrix is if you multiply some matrix A by the identity matrix, then you get matrix A back out. So we have identities in just like working with our real number system. We have something called an additive identity. You can add a number to another number and you get the original number. The additive identity is 0. I can add 0 to any number and I get the same number. We also have a multiplicative identity in our real number system. We can multiply a number by another number and get the same number. That's 1. So we can take 5 times 1 and we get 5 back out. So those things that apply in the real number system, we have something similar in matrices. It's just called the identity matrix. Now, in notation, remember that when I'm using capital letters, I'm speaking specifically to matrices. So in notation, I could say matrix A times the identity matrix is equal to matrix A, right? You just get the same thing back out. And that says I sub n only because it's n by n. So if it's 2 by 2, it's the 2 by 2 identity. If it's 3 by 3, it's the 3 by 3 identity. So the identity matrix changes. Here are examples of 2 most common identity matrices that we'll be using. Notice they are matrices where you have the diagonal of 1s coming from the top left entry to the bottom right entry, and everything else is 0. So we're going to work with or see the 2 by 2 matrix, identity matrix, and the 3 by 3 identity matrix. So we'll do an example here just to illustrate this statement. If you multiply a matrix by the identity matrix, then you get the same matrix. So we'll take 3, negative 1. Didn't know you could hear the sound. And negative 5, 2. We're going to multiply that by the identity matrix for a 2 by 2 matrix. This is great. I love it. Now, this is matrix A. We're multiplying it by the identity matrix that is 2 by 2. And what do we expect to get out? We expect to get matrix A, so let's just see that that actually works, that this identity matrix actually has that property. So if I were going to multiply these matrices together, I would start with my first row, 3, negative 1. And you know, you rotate your row and you're going to multiply it by the first column. So you would get 3 plus 0. Well, that's going to be 3. So it's working out so far. Then I'll take that first row, 3, negative 1, and multiply it by the second column in the identity matrix, 0, 1. So that's going to give me 0 minus 1, which is negative 1. And then we do that in the second row. We're going to come up with negative 5 plus 0, which is negative 5. And then 0 plus 2, which is 2. Does it actually equal A? Yeah. So the identity matrix does what we think it would do. Are we okay with that? Okay. Now, the identity matrix is an important concept to understand, that the identity matrix multiplied by any other matrix is going to give you that same matrix, because then we can use the inverse to help us solve systems of equations. So now I'm going to talk really quickly about inverse matrices and what we're dealing with here. Now, you don't necessarily have to write this blue statement down, but I just want to have it on the screen for you to look at because I've been talking about multiplicative and additive identity, but I want to talk real quickly about the multiplicative inverse in the real number system. You all agree that the inverse of 2 would be 1/2 because when you multiply 2 times 1/2 you get 1. And we use that method to solve equations. Like if we have 2x equals 6, we would divide both sides by 2, which is really multiplying by 1/2, and then we can get x equals 3. So we're going to use that same idea with matrices. So here are things you need to know about inverse matrices. Again, it has to be a square matrix. Only square matrices have inverses. The multiplicative inverse of matrix A, we're going to say is this inverse A. So I'm using a couple notation or a new notation right here. A to the -1. That just means inverse matrix A. But it follows the same definition as the multiplicative inverse with real numbers. The multiplicative inverse of matrix A is the inverse matrix A because A times the inverse matrix A is equal to not 1, but the identity matrix. So we'll call it I. And we can put that in notation as well. So some people might like it in words when they read their notes. It will actually make sense when they reread the sentence. Or some people might like to just see it in terms of the notation. If you take A times inverse A, you're going to get identity. If you flip-flop that commutative property, A inverse times A, because they're square matrices, you're going to get identity matrix again. So if you multiply a matrix and its inverse, you get the identity matrix. You'll have some questions on your homework tonight then that ask you to show that two matrices are inverses. So to show that two matrices are inverses, you want to show that if you multiply them together, you get the identity matrix. So if I were given these two matrices for A and B, I want to find the product of A and B. I kind of have an idea, again, of what should happen. Here we're just like seeing two that are supposed to be inverses for the first time. So I'll actually work it out and see that that truly does happen. Okay. So I'm going to show my work for my multiplication. I'm going to take that first row, 2, -1, multiply it by the first column. That'll give me -2 plus 3. Which is 1 for my first thing. When I take the first row times the second column, I'll get -2 plus 2. Well, that's 0. Go down and grab that second row for multiplication. So now do -3 and 1 times the first column. So we'll get +3 plus -3, which gives me that 0. And then I'm taking my second row times my second column. That will be +3 minus 2, which is 1. So we took a matrix A times matrix B, and it equaled the identity matrix. So B must be the inverse of A. That must be true. It fits that definition. Now, it should also be true, just as an FYI, that if we flip-flop them, it will also equal the identity matrix. So I'm not going to take the time to do the multiplication, but you certainly could look this over on your own time, and you could look at some problems in the book as well and see that no matter what order you multiply them, if they're inverses, they equal the identity matrix. Any questions about identity or inverse matrices that you want to clear up before we leave that for a moment? Okay, so we're going to leave this concept of identity and inverse matrix and just set it aside for just a moment. And I'm going to teach you really quickly about how to find inverses. So how could you write the inverse matrix? This you'll definitely want to add into your notes. It's basically like a formula that you'll use for 2x2 matrices. If A is a 2x2 matrix, and remember only square matrices have inverses, so 2x2 you can do by hand. So I could put this on a no calculator portion of a quiz or a test. We're going to start with some matrix A. Let the first row be AB and the second row be CD. This is your formula of sorts to find the inverse matrix. Okay, so notice I'm using my notation inverse matrix A, or A inverse. I'll let you write that down. So as you practice this, you'll get better at like what is the formula, what are the steps to find the inverse. I do expect you to know how to do this, like for Monday's quiz, you should be able to know what happens. It starts off with a scalar right here. So 1 over this piece, AD minus BC. And if you look at matrix A, those are really easy to figure out where you're getting those numbers. AD is the product of the first diagonal going down the matrix, right? Okay, so you're doing 1 over that product of that diagonal minus the product of the other diagonal, so BC. So that should be pretty quick and easy. You're making an X, you're subtracting the products of the diagonals. Okay? That's how you get the scalar. Then you have to multiply your scalar by some other 2x2 matrix, and the 2x2 matrix really generates from matrix A. So notice on this first diagonal going down with D and A, you switch their positions. Okay, so switch the numbers on that diagonal. On the other diagonal, B and C, they don't move, they stay where they are, but they become opposites. So if those numbers are positive, make them negative. If they're negative, make them positive. If they're 0, leave them 0. And so you'll just kind of follow that pattern every time you need to make a 2x2 matrix. Before we do an example with that, I want you to have a quick discussion with your small groups. Besides a non-square matrix, because matrices only work for, or inverse matrices only exist for square matrices, based on this formula that you have in your notes now, when would an inverse not exist and why? So brainstorm with your group. What part of that formula would have an inverse that doesn't exist and why? A volunteer from a group? You have an answer or a conjecture? When would an inverse not exist? Zach? Okay, so AD should not equal BC, right? That should be our rule. So when would an inverse not exist? When AD does equal BC, because what happens? Then AD minus BC equals 0. And why is that a problem for you when this equals 0? You cannot divide by 0. Okay, so here's what we have to say about that. Only square matrices have inverses. Not all matrices have an inverse. Or not all square matrices have an inverse. Okay, so in order to have an inverse, you have to be square, but that doesn't mean that you absolutely have one, because there are cases where inverses do not exist. Okay? All right. Let's practice the formula. We're going to find the inverse for this matrix A. It is first row 5, 4, second row 2, 1. I'm going to use my notation for inverse matrix A. Looks like A to the negative 1. And then the first piece of that formula is 1 over the difference of the products of the diagonals. So AD would be 5 times 1 or 5. BC would be 4 times 2 or 8. And so I know that that's really 1 over negative 3, right? So that's my scalar. Then I have to create that 2 by 2 matrix, doing a little bit of jumbling or changing. So on that first diagonal with 5 and 1, that's my A and B. Those are going to switch spots. So now my first row, first column entry is 1. My second row, second column entry is 5. On the other diagonal, those numbers, 4 and 2, stay where they are, but because they're both positive, they're going to turn negatives. So we're going to make that negative 4 and negative 2. And then to finish out your inverse, you should distribute the scalar. Okay? So my final answer for my inverse matrix would be negative 1/3, positive 4/3, positive 2/3, and negative 5/3. If it's something like divide by 3, please don't give me a rounded decimal. I would prefer an exact answer. If it's divide by 2, I don't really care if you do 0.5 because that terminates. Any questions about finding an inverse for a 2 by 2 matrix? Okay, let's do an inverse for a 3 by 3, but that requires our calculator. So without a calculator, I can only ask you to do inverse of 2 by 2. If you need a calculator, go grab one from the closet. Okay, if you have a 3 by 3 or higher square matrix, you're just going to input that matrix into your calculator. So go to your matrix menu. If you're having trouble getting to your matrix menu, ask the person next to you to assist you. And then scroll over to edit. You can change one of your matrices. I'm going to use matrix A here. I'm going to make it a 3 by 3 and I type in all those numbers. Type them in. Now, if you look in the matrix menu, in that math menu where we find reduced row echelon form and row echelon form, there is not necessarily a call for an inverse, but just think about the inverse notation that we're using with matrices, right? We're saying A inverse, and we're writing it as like raised to the -1. So then think about on your calculator, that button that you use second x to the -1, that's going to be your call to do an inverse. So once you get this matrix in your calculator, I'm going to quit. I'm going to make sure I have nothing else on my screen like typed in already. And then I'm going to go to my matrix menu and call up matrix A. I don't want matrix A, I want the inverse of matrix A. So instead of hitting second, I'm just going to type that x to the -1. And doesn't that look just like our notation on the screen? So now we have inverse matrix A and hit enter. Ooh, yikes, look at all those decimals. Ooh. Does anybody know how to change decimals to fractions in their calculator? Nicole, what do we push? Math. So don't hit second, just hit math. It's right underneath your alpha key. Hit math. The first thing that comes up, look at number 1, change to a fraction. So just hit enter on fraction. You'll get used to using this quite a bit. It's pretty nice. You want to take the previous answer, the matrix that is the inverse. You want to change it into fraction form. Hit enter. Oh, that's so much nicer. Now, if you don't have math print, the calculator might not be able to fit all the fractions in there. So you'll still see like the ... and you'll just have to like go up there and scroll over. Okay, so I'll help people that might have questions about that right now. I'm going to jot down my answer. And then I'll jot down a couple of keys that we use for this that you might want to include in your notes. And that's how you find the 3x3 matrix, inverse matrix. Those are the 2 buttons besides the regular inverse that I use. Anybody having trouble seeing their fractions, putting in their matrices, or even okay on this yet? But are you okay on this yet? Everybody doing alright? Cool. Okay. So that's basically it. Obviously, that would be in the calculator part of a quiz or a test. Alright, next thing we want to talk about is what are we going to do with the inverses? What's the benefit of having an inverse? Why would I want it? So, this slide I don't think you necessarily need to write down. Just kind of focus and pay attention with us. Do you agree that this is a method up here with the review for solving an equation? You have 2x equals 10. You can multiply both sides by 1/2, and then you would have x equals 5. Okay. And I'm showing you right here on the second step, you are multiplying by the multiplicative inverse. 1/2 times 2 is 1. That's the whole point of solving a system, right? Using inverse operations. Okay, so if I change it to matrices, and I have matrix A times some matrix X, and it's equal to matrix B, and I want to solve for matrix X, what would I do to both sides? What's that? Multiply by the inverse A. Excellent. So I'm going to multiply both sides by inverse A. Now notice on this one, it will always be true that the inverse of matrix A, that square matrix, will have to come before your matrix B. You'll see why when we do an example. But matrix A, in order to be able to multiply those, it has to be in front. But we're going to multiply inverse matrix A on both sides. And then what happens on the left when you do the inverse matrix A times matrix A. They cancel out and you get the identity matrix, right? They don't necessarily like just disappear, but they do turn into the identity matrix. And then the identity matrix times whatever matrix X is just matrix X, right? That's the whole idea of what an identity matrix does. So we can say with confidence, anytime we have this statement right here in matrices, we could skip all the way to that last statement. So if you want to write something down about solving systems with inverse matrices, those two steps might be the things that I write in my notes. If I have matrix A times matrix X equals matrix B, then I'm trying to solve for matrix X. It will always equal the inverse of A times B. So we kind of proved it right there, knowing what we know about inverse matrices and identity matrices. So when I do my work for solving systems with inverse matrices, you're not really going to see me do these middle two steps. I'm just going to go from step 1 to step 4. Okay, so let's do it with a no calculator type problem. It's got to be a 2-variable system in order for us to be able to do it no calculator. So I've got negative 3x plus 4y equals 5. 2x minus y equals negative 10. The first step is rewrite this now as a matrix equation. Note that in our previous section where we were solving, we would write it as an augmented matrix. And in the augmented matrix, we have those colons, which represented our equal sign. We're not going to see those augmented matrices anymore. We actually have an equal sign in our matrix equation. So your matrix equation is made up of 3 matrices. Your coefficient matrix times your variable matrix, and that always equals your constant matrix. And when we did augmented matrices way back in section 8.1, I talked real briefly about a coefficient matrix. Coefficient, remember, are things that are multiplied in front of variables, so we'd only pull from the left side of the equation. So in our coefficient matrix, we'll drop in negative 3, 4 to negative 1. Our variable matrix, what 2 variables are we using? X and Y. And then our constants are 5 and negative 10. And that's your matrix equation. Now, you could think about what we did yesterday, operations, multiplication with matrices, and matrix equality. If I were to multiply this first row of the coefficient matrix by my variable matrix, I will get negative 3x plus 4y, and that would have to equal on the other side 5. So there's my first equation. And the second row would be 2x minus y equals negative 10. So that's the second equation in the system. These represent A, X, and B. So now we want to just solve the system. If we have matrix A times matrix X equals matrix B, then the solution to the system will be the inverse matrix times B. So without a calculator, you'll need to find the inverse. So first thing I would do is find my inverse A off to the side. I'm going to do the AD minus BC in one step. So that'll be 3 minus 8, which will be negative 5. So I'm doing the inverse for the matrix A, which is the coefficient matrix. Positive 3 minus 8 is negative 5. And then switch the first diagonal. I should have negative 1 and negative 3. Change the signs of the second diagonal with B and C, so negative 4 and negative 2. When I distribute, all of those are going to become positive, and they'll be fractions with denominators of 5. So 1/5, 4/5, 2/5, 3/5. Are we okay with what I did? Okay, now you have the inverse A, multiply it by B. Here's where you can kind of see why inverse A has to be first. This is a 2 by 2 matrix, and my constant matrix up here is 2 by 1. So the only order that I could possibly multiply those matrices is inverse A times B. So I have my 1/5, 4/5, 2/5, 3/5. I'm going to multiply it by 5 and negative 10. And if you have fractions in your inverse matrix, that's no real cause for alarm. That's totally possible and probable in a lot of instances. Take your first row, multiply it by your column in your constant matrix. That would be 1/5 and 4/5. And then we'd have to add. So that would be 1 plus negative 8. So that first entry is negative 7. And then take my second row, 2/5 and 3/5, multiplied by 5 and negative 10. So 2/5 times 5 is 2. 3/5 times negative 10, that'd be 3 times negative 2, which would be negative 6. So negative 4. And now I have solved my system. Negative 7, negative 4.
Why do we learn this? Do people prefer to do this other than just like solving the system?
Yeah, so it would just be like, like a difference of preference. But I think what you need to think about with matrices is like the whole thing about matrix or matrices is how organized it is, right? So I'm thinking I would use matrices if I had a very large system. Like obviously I'm not going to give you a 20 variable system to solve because you don't have that kind of time. But I can ask you to see how this works for a 2 variable system. But we could program a calculator or program a computer and very easily set up matrices to solve it, which would, I think, be a lot easier than the algebraic method. So I think you have to think about it in terms of like a big picture here, that like we'd be working with things much more challenging than what we see. We have to do small, easy ones. So yeah, you're like, I've been doing solving systems since algebra, why wouldn't I just solve the system? It takes me less time. I get it. But we want to see the big picture here. There's probably a place for matrices, and you need to understand why it works. Good question. Anything else? Okay, just really quickly, my last example is a 3 variable system of solving linear systems. So in this one, remember that you would take matrix A times matrix X equals matrix B. And your solution would be X equals the inverse of matrix A times B. So what I would do in my calculator is type in my coefficient matrix, type in my constant matrix, and then call for the inverse of matrix A times B. So I'll just show you really quickly. I'm going to be typing up in my calculator here. I'm going to go to my matrix menu. I'm going to edit matrix A, which is already 3 by 3. And I'm going to do 1, -4. Oh, this is the same one. Cool. I already did matrix A. I knew I did that for a reason. It's already in there, right? The inverse that we did. So then what I really need to do is go to my matrix menu and edit matrix.
Go back. Make it 45.
I do? Ah. Yeah, look at it when I type. Oh yeah, because I was typing and then I noticed it was the same. Thank you, Elise. Okay, so then you go to your matrix menu. You would edit matrix B. In this case, this should be your constant matrix, which is that column matrix on the other side of the equal sign. So I've got my -4, -23, and 38. So that's a 3 by 1. And once you get those things typed in, now I just got to call for my matrix A, do the inverse, and multiply it by matrix B. Oh, I have a solution. That was pretty easy. So now Lauren might be able to see, like, if we have some really big systems, this, typing in some data into some organization is going to be a lot quicker than trying to actually solve the system. And think back to chapter 7, linear programming. All of our linear programming problems had like 2 variables, but in the real world, there's a lot of things affecting a decision. So you probably want a program to solve it. So that would say -3, 4, 3. Okay. You'll have a homework assignment. I know you only have about 5 minutes left, but you could pull that out. If you need my calculator to do matrices, you might look on the homework assignment. Are there any specific questions that ask you to do work in your calculator? If you have a question about last night's homework or one of the previous assignments, now is a great time to ask those questions. Or if you're planning to retake Chapter 7 test, you could see me with any questions that you have. If you're having any calculator issues, also ask me now.